So hello everyone, welcome to our second hidden webinar of the year. It's a pleasure today to have with us Julia Harz from TU Munich, and she's gonna talk about kaon physics and the lepton-number violation. The stage is all yours, Julia.
Yeah, first of all, thank you very much to be invited to this webinar, of the hidden webinar. And yes, Jose Miguel already said, I'm talking about constraining lepton-number violating interactions with the rare kaon decays. And this is your recent work done in collaboration with Frank Deppisch and also my PhD student, Cora Friedel. So let's start. So what is the outline? So as I was told that also the hidden network is also for training of young researchers. I will start with a more overview and with more introduction. So first I will start with the motivation. So the neutrinos as a window to new physics and why in this respect lepton-number violation is interesting. In the next step, I will then talk about lepton-number violating interactions, so different operators that exist, the testability, and the connection to leptogenesis. And the last and main part of my talk will then be about the rare kaon decays. I will give a short recap about the rare kaon decays in the standard model. I will talk about lepton-number violating interactions in kaon decays, how one could potentially test them with experiments like E949, KOTO, or NA62. I will talk about the complementarity of different constraints, and in the end, I will give an outlook to a possible UV-complete model with respect to leptoquarks. So let's start to the introduction and the motivations. And I think everybody in this webinar is inspired that neutrinos are hidden particles, elusive, invisible particles. And what we know from them is somehow that they are the standard model misfits. They are not really fitting in, and we want to find out how we can make them fit. And so the question is, what do we know about neutrinos? And of course, also especially since 2015, I think also not only within physicists, but also moreover known are the neutrino oscillations. And here you see, so a neutron beam is here shot through the underground until the detector, and then we see here an oscillation of the neutrinos. And what we know is that this oscillation in the flavor of the neutrinos is basically only possible when the neutrinos have masses. Of course, then the question is, how do they get their masses? Because also what we know from the standard model is that the neutrinos that we have in the standard model are basically massless. What we also know from the neutrino oscillations is that neutrinos mix, so here with the typical UPMNS matrix, so we have here a mixing between the flavor states to the mass eigenstates. And as I just have said already with respect to the oscillations, we know that they depend here on the mass differences of the neutrinos. So we know that they need masses, but we also know, at least relatively, the different masses, the different mass differences between different neutrinos. And as we don't know the absolute mass, we can here get two possible orderings, either here the normal hierarchy or the inverted hierarchy. So in principle, even though we don't really know how they fit in, we already know quite a lot. So the main question is, of course, how do they get their masses? What nature do neutrinos have? And for example, are they their own antiparticles? And so on. So how does then lepton-number violation come into the game? So we know now that we need to generate somehow masses for the neutrinos. And what, for example, could help would be right-handed neutrinos. So now, if you imagine, it makes sense, right? I have the lepton doublets, for example, the fermion doublets, and I also have right-handed quarks. So why should I not have a right-handed neutrino? Okay, so what I can do is I can here add right-handed neutrinos to the standard model, and then I can add here a Dirac mass term, and you see, thanks then to the Higgs mechanism, and here in orange are the hypercharges, then I can get here a Dirac mass. This is in principle nice, that I can get with this kind of mechanism a mass for the active neutrinos. However, what is not so nice, or what is surprising or might not be expected, is that we get here tiny Yukawa couplings out of the known mass that we need roughly for the neutrinos, for the active ones, and electroweak scale. And additionally, another reason is now if we already add the right-handed neutrinos with hypercharge equals 0, then basically lepton-number is not an accidental symmetry anymore as it would be without the right-handed neutrinos in the standard model, but we need somehow, in order not to have a Majorana mass term, somehow construct a symmetry that basically keeps the model lepton symmetric, or there's no lepton violation in the standard model. Or in other terms, basically by plugging in a right-handed neutrino, what we basically also get, or what we can also directly write down, is a Majorana mass term. Why was this otherwise not possible with the particles in the standard model? This is, of course, because of the fact that the neutrinos are chargeless, and therefore this is the first here where I can basically put the Majorana mass term. So the problem is now, again, if we look at the hypercharge, we see here that we cannot write down a Majorana mass term with respect to the active left-handed neutrino or to the left-handed neutrinos. So this is basically that I need to create the masses via loops. And for example, if I write down here, I need to write down a higher dimensional operator. For example, here, like the typical Weinberg operator with 2 lepton doublets and 2 Higgs doublets, where here hypercharge is again 0. And I would then create the mass, so to say, here via loops. So this is a higher dimensional operator that I would then get for the Majorana mass. And additionally, what of course it also requires, or what it means, that now I really have an interaction that would give me lepton-number violation that I actually then would like to see somewhere to test if I have a Majorana or a Dirac nature. This brings me to the second part already. So this is the motivation to look into lepton-number violating operators and lepton-number violating interactions and their implications. How can we test them? And so first of all, I already have mentioned that, okay, we can have lepton-number violating actions, for example, higher dimensional operators like the Weinberg operator. This is the 5-dimensional one here. Now in orange, you see the mass dimensions. So here 1.5 for the fermions, 1 for the Higgs, gives me perfectly 5. So I have to scale it with 1 scale in order to get mass dimension 4. And then basically it is known that if I want to have higher dimensional lepton-number violating interactions above dimension 5, then it always goes in odd numbers, 7, 9, 11, etc., etc. And basically here already lists or surveys exist at least up to dimension 11, here especially by these 2 groups here, that really made a survey of all lepton-number violating interactions. And this is also, for example, where you see here the nomenclature that I use is basically also from the de Gouveia and Jenkins paper. So if you wonder what is O14b, I use it still that I can easier refer to it, but this is basically where the name comes from. So, okay, so what we see now here, we can have, of course, the usual Weinberg operator, but we can also have 7-dimensional or 9-dimensional operators. And so to say here, this is of course only a few examples, but in principle we have over 100 operators up to dimension 11. What one should keep in mind is the following, that also higher dimensional operators can now introduce via loops masses for or in terms of the Weinberg operator. What do I mean? So for example, if I start here with a 7-dimensional operator, then via loops, I can also again create here the usual mass mechanism, or here this is the mass mechanism. So here the neutrino mass, I have 2 Higgs wefs, so it scales with wef squared over the scale lambda. And then I can do the same here for the 7-dimensional one. So now let's have a closer look at 3a and 3b. What's the difference? So you see here that the SU2 contraction is slightly different. So here we contract L alpha, L beta, and here we contract here L alpha with a quark doublet, and here the lepton doublet with a Higgs doublet. What does it imply? It implies now that if I want to create a neutrino mass or a Majorana mass, that now these contributions from higher dimensional operators are differently suppressed. And where does this come from? For example, if we look now here in this operator, we have here, for example, L alpha and L beta. So this means if I look into my lepton doublet, I always get contributions, for example, of a neutrino and an electron. If I now want to create a Majorana mass, then I somehow have to swap the electron into a neutrino. So this is the reason why I get here this additional loop. And then here I have here the quark doublet, for example, and here the down singlet. And also this I have to combine somewhere to close a loop. So this is, for example, why I need here this additional mass insertion. This case is a little bit different here for O3b. So you see here now with L alpha, L beta contracted with the quark doublet and the Higgs doublet, I can directly get here the neutrinos, and this is why this contribution is less loop suppressed than the other one. And then I can do the same games with all different operators, or here, for example, for the 9-dimensional one, it on the one hand contributes via loops to the 7-dimensional one, which one sees here, but at the same time also again via loops to the 5-dimensional one, and you see this is now in contrast to the other much more loop suppressed. So you see also higher dimensional operators larger than 5 can give contributions to the neutrino mass. So then the question is, how can we basically test lepton-number violating interactions? So in order to know, in case it's a Majorana type, what is the operator behind? Is it via loops or is it directly the standard Weinberg operator? And this, for example, the holy grail of lepton-number violating interactions is usually here the neutrinoless double beta decay. So here 2 neutrons into 2 protons and 2 electrons. And then we have here again the different contributions, either the standard mass mechanism that we just have seen, or the higher dimensional contributions, which is here the long range contribution, the O7, or the O9 that directly contributes here to neutrinoless double beta decay. And yeah, thanks to neutrinoless double beta decay experiments, we have stringent limits on the half-life, and then can thus set limits here on, so to say, the effective neutrino mass m beta beta, which is here this contribution, for example. And additionally, we have then here the nuclear matrix element and the phase space factor that then adds on top of it to really cross-link the m beta beta to the half-life that we hopefully observe at some point, and don't set only limits to this. The drawback, what one should mention for neutrinoless double beta decay, that it's a very sensitive probe on the one hand, but on the other hand, it only probes the first generation. So this is basically the limitation of neutrinoless double beta decay, because we only have here the electrons and the first generation quarks. So now what we also, I guess, all know is the so-called Schechter-Weyl theorem, and this we can also now connect easy to what I've said with respect to higher dimensional operators. So I've just shown you that basically via loops, higher dimensional operators can always contribute to lower dimensional or to the Weinberg operator. And this is basically here also visible here in the Schechter-Weyl, the black box theorem, that any delta L equals 2 operator will induce to a certain level a Majorana mass contribution. And what we have also seen, it doesn't mean that this is the dominant contribution. So because, for example, if you have a higher dimensional operator, it can still lead to neutrinoless double beta decay, but so to say, due to these loop effects that I've shown you, the contribution can be to the neutrino mass extremely small. So this means that even while neutrinoless double beta decay gives us a hint for lepton-number violation, it doesn't necessarily mean that the mass mechanism is the most dominant contribution. So then what else? So this we have seen already, the standard mass mechanism, but we can also have, so to say, long range or non-standard contributions. And let's look again at the dimensional 7, or this so-called the one O3b that I picked before. And what we see now here, we have on the one hand a hadronic current, and on the other hand here a leptonic current. So what we can do now, we can write down this current structure here. The small j is the lepton sector, and the big J the hadronic sector. And then we can basically have different current structures in the two currents, and here with an effective thing, which then can here be directly translated into the expression for the half-life. And then what was done, one can set here limits on the different effective couplings depending on the currents, on the chirality structure and the currents. And this is basically another way. So for example, if one assumes now that they are long-range contribution, then you can also constrain them directly as a dominant contribution from neutrinoless double beta decay. And then what we see is the following picture. So we concentrate now only on the upper bar of this graphic. So here you see simply different operators. So here in blue or purple are the 7-dimensional ones, in green the 9-dimensional one, and in magenta or purple the 11-dimensional one. And what we concentrate now is only here the upper bar. So we see here the upper bar. So this is, so to say, if we assume only for the 7-dimensional or 9-dimensional the non-standard mechanism. This is if we would now observe neutrinoless double beta decay, the new physics scale that we get. So as I just showed you, we would from the half-life get a limit on the effective coupling and hence on the scale of the operator. And this here we can now compare, for example, if we would have only the standard mass mechanism. This is, so to say, here the orange diamonds that you see. So we can compare now if we have one operator and it contributes not only directly to neutrinoless double beta decay, but also via loops to the Weinberg operator, what is the dominant contribution? And you see now here for first generation couplings, for many of the operator, it is indeed this non-standard mechanism. And here the mass mechanism is due to all the loops suppressed. This picture changes now if I assume also third generation couplings in my loops. Now you see here that the standard mass mechanism is also often the more dominant one. So now we have looked before, for example, to O3b, to one of the examples that we discussed that generate neutrino masses. And here, for example, you really see that for O3a, before the mass mechanism is less dominant than the non-standard mechanism. And then if we go to third generation, this picture swaps. So this means, of course, that in the end, it also depends on your flavor structure, or of course also on the actual UV complete model that you want to look at. But bottom line here, depending on which, so to say, what is the dominant, if you have an observation of neutrinoless double beta decay, and for example, you have a higher dimensional operator, it would always contribute to the lower dimensional ones too, and then you can compare what do you expect will be the dominant contribution to neutrinoless double beta decay, depending, for example, on first or third generation couplings. Okay, so now you might wonder, what are these bars? So before we only looked here at the upper limits and the diamonds, now we want to wonder what are these bars here. And the bars here show basically the implications on leptogenesis. So I don't want to go into detail. I just want to, for people who haven't seen it yet, basically see what it means. So I think also last week, if I'm not mistaken, you had a talk mainly on leptogenesis, so I will make it short. So the idea of leptogenesis is simply that first I create a lepton asymmetry, for example, by heavy neutrino decays. I have at the same time not only the decays, but also other processes which are the so-called washout processes. Then these processes compete. I create a lepton asymmetry, and this then via the Falaron processes is translated into a baryon asymmetry. Or basically in a more pictographic way, this is what I just said. We have a lepton asymmetry that we want to create via standard model processes they can, via the scalarons, translate into a baryon symmetry. And what I usually have is a competition between the lepton asymmetry generation and the lepton asymmetry washout. So now we assume we see, for example, neutrinoless double beta decay or any other lepton number violating process. What would then be the implications on the lepton asymmetry washout? So what we did here is we calculated the lepton asymmetry washout under the assumption that we have a pre-existing asymmetry in our universe. So this basically does not include additional CP violation. And then here, this is the operator that I take as an example. Again, this O3b operator. I write down the typical Boltzmann equation for my lepton asymmetry. I can rewrite here the reaction rates in terms of the scale of the operator that I would get in case of an observation of a lepton number violating interaction. And then I can solve the Boltzmann equation, or I can make an estimate of the washout by comparing the washout rate over Hubble. So in terms, if the washout is large, this would mean, or so to say, the washout rate is larger than Hubble, then it means that the wash is highly effective. And by doing this, I can then get independence on the scale of the operator that I would get in case of a measurement, the temperature interval where the washout is highly effective. So this was the scale that we looked at before. So this is the upper limit, the limit of the EFT, and this is the lower scale where the washout is effective. And this is now basically where the bar comes from. So this is here the upper limit given from the scale. And then you see that many of these operators would imply a washout of a pre-existing asymmetry at a higher scale, really down to the electroweak scale, which could possibly basically put baryogenesis or leptogenesis models under tension in case, so to say, they would create a high or would create an asymmetry at a high scale. So are there other ways to test lepton number violating interactions? So the prime example is neutrinoless double beta decay. Another possibility is, of course, at the LHC. So you see here, this is again would correspond to a 9-dimensional operator. For example, here, 2 protons into 2 same-sign lepton and jets without any missing energy in order to make sure that we are lepton number violating. And then you can see here, this is the LHC cross-section. This is the resonant particle here. And so to say, here you see what is basically already excluded. And here, this is, so to say, the exclusion limit from CMS. So this is really just scratching from top, where lepton number violating interactions here get excluded from the LHC. But on the other hand, what we could also show, again, if we look into the washout of such a process, that here, if we would measure a lepton number violating interaction at the LHC, that this would possibly falsify high-scale baryogenesis models, or would put them at least under tension to see if, so to say, the CP asymmetry was, for example, generated at a lower scale. So this is in principle quite nice, the interplay between LHC and neutrinoless double beta decay, but so far what we did was basically only at a EFT level. And what we are also currently doing here in collaboration with Michael Ramsay-Muself and his 2 PhD students, Simon and Sebastian, that we put this at the test in a more complete model or in a simplified model. So to say, this here is the simplified Lagrangian. So you see here a Majorana fermion and here scalar S, and it would give both contributions, once to neutrinoless double beta decay, here the typical 9-dimensional or looks 9-dimensional operator, and here this typical collider signature, 2 same-sign leptons and 2 jets. And here GQ is here, and GL the corresponding couplings, either the scalar to the quarks, or here the coupling here to the leptons with the L. And this you can see here in the plot. So we basically wanted to see how good our estimate was before in the EFT analysis. So here GQ and GL. here is the collider limit, what you can see from this signature, and you see here the results from neutrinoless double beta decay. You see there's a kind of a competition, but for high coupling, so to say, the neutrinoless double beta decay in this area is more dominant. And we also checked carefully the leptogenesis calculation, and we could also see again that here in all the red, basically we would get a lot of washouts that really you would not create the right baryon symmetry in this red area. So basically a measurement of the LHC or future colliders or current and future neutrinoless double beta decay would really conform the EFT analysis that we did before, and also for couplings that are smaller and not around order 1 that we assumed before. So now we have seen that it's interesting to test lepton-number violation from neutrinoless double beta decay, also from the LHC. And now the next question is basically what kind of other probes are there? Or is it, for example, possible to probe lepton-number violating interactions in terms of kaon decays or meson decays in general? And for this, I want to give a short recap about kaons in the standard model, just to refresh our minds about kaons. So this is where everybody is familiar with. So this is this typical 16-plet for the pseudoscalar mesons. So you see here we have the typical pions, we have the kaons and the demesons. And we can distinguish them between pseudoscalar ones and vectorial ones, where here we have L is the orbital angular momentum of the Q prime pair. And then here this is basically S is 0 or 1, depending if the spins of the two quarks in the meson are parallel or antiparallel. And then you see here, for example, if we have S equals 0, that we then here, and L equals 0, we get here that J equals 0. And then we see that this is basically odd under C, under T, and even under charge, such that the whole kaons, so to say, are odd under a CP transformation. And what we want to look now in particular at are the K plus and K0, where we have both an anti-strange and, depending on K plus, a U quark or a D quark. So now let's first have a look to the neutral kaon, the K0. And so as they are neutral, they can basically mix. So we have the neutron, the kaon oscillations. So you see here that basically via these weak interactions, a K0 can oscillate into a K0 bar. This means then here basically that from these states, the K0 and K0 bar, we can create CP eigenstates that are either even or odd under the CP transformation. And then, as we have reminded ourselves, the pion is also odd under CP transformation. So this is why the K1 would mainly or would only decay into 2 pions, while the K2 would basically decay into 3 pions. And due to phase-space suppression, we would expect here that the decay into 3 pions are slower than the one into only 2 pions. Okay, but then in 1964, what happened is that it realized that also that not all K2 or K1 were only, so to say, decaying in the one that one was expecting, but that there was a kind of a mixture. And this is basically, so there's a small indirect CP violation. So there's a mixing between the CP eigenstates, such that then this mixture of these 2 states was then, with this kind of indirect CP violation, was then called K short and K long, depending on the decay time of the kaon. So then, if we now look into the standard model, we know now we have the K long, we know now we have the K short, and we know we have the K plus and K minus. And you see now here the contributions, the penguin diagrams, and here the box diagram for K plus decaying into the pion, and here with the neutrinos. And this here is the contribution for the charged, and this is, so to say, for the K long, so the linear combination of the K0. What directly appears crucial is here that in the K plus we have a Jim suppression. So here we do not only have the U, but also, for example, the charm quark. And this is the reason why here these diagrams basically get suppressed due to this kind of cancellation. So this is basically also why in the standard model the contributions to these processes are expected to be extremely small due to the Jim suppression. The other one that we will now realize is that we have here only the imaginary part for the K long. And this we will also see in a bit later in more detail, that for the K long, as you have this kind of CP violation, we always will pick the imaginary part within the standard model. So there's no real part, but only, so we need, in order that this K long to happen, we need here a CP phase. And then, okay, we can calculate it. What do we else have here? We have here the lambda is the Wolfenstein parameter. We have then here the XTPC are different higher order corrections to the full calculation. But what is now important is this kappa. And so this kappa, so if you now imagine what we want to do is we want to calculate the hard process, which is the one here in the middle. But we, of course, also pick the nuclear physics from the kaons and the pions. And this is, so to say, here, while this bracket here only shows the hard physics, the form factors or the nuclear physics is here embedded in the kappas. And now why are especially here the K plus to pi plus in two neutrinos so interesting? It's so interesting because especially in these processes, one can reduce the hadronic uncertainties extremely good. So this is also why they are called the golden channels. Why is this the case? The case is the following, that what one can do, and this was, for example, also pointed out by Mesky and Smith in 2007, that here we can relate the K plus and the K long here to the mixing to the CKM matrix. And this part here includes now the nuclear form factor. But why is this now so precise, what one naively would not expect? And the reason is that one can relate the nuclear form factors to a more frequent decay, where I have here a charged lepton and a neutrino. And as this decay is more frequent, I have here better statistics and a better handle, and one was able here to relate, so to say, to build here the ratio such that the uncertainties in the hadronic part are extremely small. And this is also why it's so interesting to look exactly into the K plus, into neutrinos and the pion, because of these small uncertainties. And what is the other motivation? The other motivation is, of course, that I have in the standard model extremely precisely the theoretical prediction, both for K plus and K long. And on the other side, I have experiments, and especially also future experiments, that will really probe these processes to an incredible precision and almost down to the standard model sensitivity. So the best limit here is basically E949. Then there's the new data from NA62. So far there's only within the publication the upper bound, and then also here the limit from KOTO. And if you compare this with the standard model values, you see that there's basically still room for new physics that can basically hide in these uncertainties. And as these processes are, so to say, called the golden channel, because these uncertainties can be reduced, and NA62 will probe this almost down to standard model sensitivity, we were basically asking ourselves what extent can new physics, and especially lepton-number violating interactions, hide in the kaon decays. Because if we simply measure here the pion and we don't know what the neutrinos are, of course the neutrinos can be also of Majorana type and basically have an admixture or some lepton-number violating interactions on top of the standard model contributions. So then this is what we are now doing. So to say here we have the kaon, we have the K plus and the pi plus. And so now you see that basically I can now imagine that I have lepton-number violating interaction, and here the neutrinos are of Majorana type. And here I put now the 5-dimensional operator and this O3b, the 7-dimensional operator that I introduced already in the beginning. The problem here for the 5-dimensional one is that I similarly get a Jim suppression. However, this is not the case in the 7-dimensional operator. So here I have no Jim suppression. And in contrast, for example, neutrinoless double beta decay, it includes also the first and second generation. So basically, kaon decays are able to probe another flavor sector, in contrast, for example, to neutrinoless double beta decay. Of course, one has to be careful because, of course, we are not necessarily know that if we measure measure basically a deviation from the standard model, that this is necessarily lepton-number violating. So this is basically be careful, or needs an additional way to figure out if it's really lepton-number violating, because we are agnostic here on the nature of the neutrinos. So then let's ask the question, how are higher dimensional operators constrained by these meson decays? And so, for example, what we can have is the same sign leptonic final state. So you might now wonder, why did I not mention from the beginning the same sign leptonic state? Because there we actually could know that we have lepton-number violation. And the reason for this is, even though we would test lepton-number violation directly, the constraints are extremely weak in contrast to neutrinoless double beta decay, because here the 9-dimensional operator is the one that is underlying. Then we would have now the ones with neutrinos in the final state, either the decay into a neutrino final state, or then here basically from a K plus into a pi plus and neutrinos, or here a K plus into a charged lepton and a neutrino. And what we will focus on now is, so to say, here the neutrino final state. And the reason is A, because we can constrain it with current and future experiments. And B, we don't expect this big suppression that we would have here for the 9-dimensional operator. So what do we do? So now we want to calculate the lepton-number violating interaction. And so we have here the kaon and here the pi, and here I want to comment on that you might be now confused because here it's an S bar, but this K basically connects to both K plus and K0. So this is why this is basically here for the K long. And now let's pick one of the higher dimensional operators. So we have here the O3b, which we can here put in into one of the possible SU2 contractions. And then we directly see we get the 2 neutrinos and the 2 down-type quarks that we actually want to have here. However, now we have to consider that we have different spinor contractions. So we can here get a spinor product here of the quarks and leptons, but also here the mixed ones with leptons and neutrinos. But what we can do is we can Fierce transform it such that we can only get pairs of quarks and leptons as we need here for this matrix element. So what we will get here is this contribution, an additional tensorial one. But if we have neutrinos of the same flavor, so we don't assume flavor violation, then this basically will vanish. Okay, so this is now in the Weil format, but now we go from Weil into Dirac. Now you see then we will get here a scalar contribution and here this additional contribution, which will vanish because if we put it here into this matrix element as the kaons and pions are pseudoscalars, this basically will give no contribution. So what we will end up then is here with a scalar contribution, and we can identify here this part with 1 over lambda to the cube, which is the scale of this operator. Okay, so why did we want to have it now in this form? Because we have here the matrix element. And so we have here the VEF coming from the operator, the scale. And now we have here this part here that we can rewrite now in terms of the nuclear form factor. So this here is the nuclear form factor. So it basically takes care of it that the quarks are basically in a kaon or pion. And here the mass differences first of the constituents, but also of the bound particles. And then we can rewrite the matrix elements basically also in all our known variables. So the form factors are known. And we can get then here a two-dimensional or a differential distribution of the branching ratio or the decay rate in terms of S and T, while these are the Mandelstam variables. And S is, so to say, here the energy loss by the neutrinos. So this is here the energy, so to say, here the momentum of the kaon minus the momentum of the pion. So we used for the analysis form factors, but one can also match this onto chiral perturbation theory. And this is, for example, what was done in this recent paper by Lima and Schmidt, for example. Okay, so what do we get out of this now? So what we will get now, so let us remind us, we had here the scalar current from the lepton-number violating interaction, but we have also, for example, in the standard model, the conserving lepton-number conserving current, which is a vector current. And what it will lead to now, if we integrate, we will realize that it gives us a different phase space distribution. So this here is the kinetic energy of the pion, and this here the distribution. And you see here for lepton-number violating in red, it basically peaks for lower energies, and here for the standard model at higher ones. So this here is only our theoretical distribution based on the phase space. And then we have here the different signal regions, where, so to say, here E949 is sensitive to. And you see that it's much more sensitive here in signal region 2 and 1 to the standard model current than to the lepton-number violating current. And here in dashed, we could extract from the E949 paper experimental acceptance. And this is basically how, after our theoretical distribution, how the experimental acceptance looks in the end, coming from the experimental limitations. But bottom line, what you see is basically if we would have enough events and we would have here additional events of a lepton-number violating or scalar current, then we would basically under the assumption that we have a certain event number in signal region 1, and we have here the additional events in signal from the lepton-number violating interaction, we would basically naively expect more events in signal region 2 that we will have, because here the lepton-number violation interaction will only give a small contribution. What is very nice at the E949 experiment that they already gave limits for a vector or a scalar current. So this was what we could also use then for our analysis. However, one catch was that they, for the scalar current, even though we know we get a contribution from the standard model, they did not include, so to say, the additional standard model contribution that we necessarily have. So basically, both values are always not super correct if you assume both interactions at the same time. Okay, so then with respect to KOTO, here I mentioned already the CP behavior, the CP the CP interactions for the kaons. And interestingly, this is what I've said also in the beginning. In the lepton conserving mode, we have a vector current, so it will pick up in the branching ratio the imaginary part. However, if we have now here a scalar current, it will pick out the real part. So basically, in our analysis, we do not need to include an additional CP phase, because due to the scalar current, we will get also a contribution to K long. Again, here for KOTO, the different phase-space distributions overlaid with a signal region, here in the transverse momentum of the pion. And unfortunately, here also, of course, it's nicely for the standard model, but here the lepton-number violating interaction peaks here for lower momentum. And then last but not least, how does it look for NA62? So here you see now a similar picture. In blue, the standard model, and in red, the lepton-number violator interaction. Now violate also with all the background, and I find it really impressive what people do, because here this is scaled by a factor 10 to the 10, right? So the background is much larger. And you see a similar picture that basically the experiments are more sensitive to the vector current than for this current. But what we also did here is a summary, so to say, just from the phase-space distribution, how much percentage in the different signal regions in the different experiments we would assume for a vector or a scalar current. And there you nicely see, for example, in signal region 2, what I mentioned already before, similar for E949, we have more contribution from, or we have similar contribution from lepton-number violation and standard model, while in signal region 1, it's going much more down than the standard model. So the question, and the same here for E949. So the question is really if, in a future perspective, if one can basically gain more out of there, or at least basically provide also scalar current limits for these experiments, what E949 already does. So then in order to basically get a better idea how we basically could constrain it in the parameter space, we also wanted to see, because of two-dimensional distribution, how much it depends, so to say, also on the pi in energy and the energy of the neutrinos. But you see there's not more exotic structure. So basically for a fixed S, so to say here, this stays pretty much constant for all pi momentum. But generally, so again, the picture that for lepton-number violation, we expect more events in signal region 1, while for lepton-number conserving, we expect more events here in signal region 2. So now, what we do now is we have the different distributions. We see they look different, but of course now we are also curious about the new physics scale that we could actually constrain from these meson decays. And you get here already an idea for the branching ratio for lepton-number violation for K plus and K long. You see already in the ballpark of around order of 10 TeV. But of course, this is a rough estimate because, as I mentioned before, we get both contributions to this branching ratio, the standard model contribution and the lepton-number violating contribution. And so basically the number of events normalized to all events then depend on these two branching ratios and then multiplied by the corresponding acceptance factor of the experiment. And here, at least we could take it out from the E949 experiment, the relative acceptance factor of lepton-number violating and standard models of scalar and vector current, and could then here basically set a limit on the scale of the lepton-number violating interaction. But again, keep in mind, it's also not 100% perfect because they only gave us a vector or a scalar limit. So this is then what we get here. So this is basically the value we should look at. So this is, so to say, the most trustworthy value that we can get out of it with respect to other experiments, because we get really the differentiation between the current structure. So we can here basically already from kaon decays constrain the scale of around 10 TeV. And you can see we can do the same here for different operators. And you see also here now the scale that I've showed you in the beginning. If we also now include the right-handed neutrino, it can either be more constrained by the right-handed neutrino mass, like in this case, or it can be the opposite, that the contribution to the neutrino mass is smaller. But again, this of course then depends on the UV complete model. So to say, this is why these values here are more direct than the conclusion of the contribution to the neutrino mass, because this highly depends on the actual model in the end. And again, to stress, even though, of course, we cannot ensure that we have lepton-number violation, we can set limits on it, and we can even set limits on different flavors than the most constraining neutrinoless double beta decay. And you see here our projections for NA62 and KOTO, so it can go up of almost 20 TeV. So we did a similar analysis for the charged final states, and oops. Okay, so we did a similar analysis for the charged final states, and so you see here now K plus into a charged lepton and a neutrino, and you see here again that here the scale is much lower because the constraints is less, but also here, but on the other hand, the constraints on the neutrino mass is smaller. So what is as a summary? So as a summary, you see here that in this case, so to say, we can set already a large limit on the scale. We did another comparison with respect to B mesons. Here, it looks different. The scale is less constrained. So for example, here one could still imagine a nice cross-link with respect to the LHC range, while this is only maybe future colliders, but out of LHC range. And also, last but not least, I want to make the connection to the washout that I introduced in the beginning. So we also compared this with basically a washout scale. So you see also here the lowest scale until which a high CP symmetry would be washed out goes almost down to the electroweak scale. So here's the under the assumption that we would basically at some point know that the lepton number violating interaction is behind, we could also get here prediction of a large lepton asymmetry washout. And okay, here in contrast to neutrinoless double beta decay, of course, we are much lower for the other scales than with neutrinoless double beta decay. But again, you see here we are limited to a specific flavor structure. Okay, so in the last, I guess, 2 minutes, I want to make a quick outlook to leptoquarks. And the reason is the following. The reason is twofold. First, because when we wrote our paper, this paper simply came up. And on the other hand, I want to comment again on this connection to the meson and the neutrino masses, because we saw, for example, with the operator 3b, that neutrino masses would be suppressed. So what we have here is now a Lagrangian, so to say here with 2 leptoquarks. And if we would basically integrate out heavy fields, it would correspond again to our operator O3b that we looked at and another operator. This operator would give us here the charged final state and a heavily suppressed neutrino mass, while this operator would give us the kaon into 2 neutrinos and a less suppressed Majorana mass for the neutrinos. And so in this estimate, basically here, if you would see something in the rare kaon, what would it imply for the neutrino mass? And this we looked at. So here, basically, we took the usual loop contribution to the neutrino mass. We have here the corresponding 2-loop diagram. And so to say, in order to get the neutrino mass in the right ballpark, what we need to do is, so to say, basically suppress the 1-loop contribution and have a non-trivial flavor pattern in order to get the neutrino mass only at 2-loop. So basically what it would be, mean that in case we see some leptoquarks and rare kaon decays, it would then, if this is the only underlying operator or the only underlying model, only underlying contributions in the Lagrangian, it would imply a non-trivial flavor pattern to explain the smallness of the neutrino masses. So this brings me to my conclusions. So first of all, I discussed Majorana neutrino masses, and that they can basically appear not only from the Weinberg operator, but also from higher dimensional operators. That the strongest limit so far comes from neutrinoless double beta decay, but is limited to first generations only. That the rare kaon decay is in principle also a probe of lepton number violation directly if we look into the charged final states, but this is only weakly constrained as the underlying operator is the 9-dimensional one. Another possibility is to look into the effects of lepton number violating dimension 7 operators into the kaon decays, but here we cannot have a final conclusion on lepton number violating, but we can simply put limits on our new physics scale. I showed you basically that depending on the lepton number violating or lepton conserving interaction, we will get a vector or a scalar current that I might be able to disentangle somehow at these experiments, that I can here make the connection of lepton-number violating that interactions that can imply a strong lepton asymmetry washout. And I gave one example of these operators in terms of a leptoquark model, where, so to say, here one would, for example, have a non-trivial flavor structure. And with this, I would like to thank you for your attention.
Thank you very, very much, Julia. Now, anyone that wants to ask a question, please simply raise your hand, and we will we'll give you voice. So, I have one question.
Mm-hmm.
So, Sergey, you can ask now.
So, Julia, nice talk. Thank you.
Thank you.
Now, about the washout effects, in which flavor, I mean, they are dominant, actually, because, I mean, the asymmetry can be generated in the tau, the mu, and the electron flavor.
Mm-hmm. Okay, so very good. I mean, this is basically because, yeah, I wanted basically to concentrate on the kaons. I was not focusing on this. Of course, this is true. So basically, what I've shown here is, so to say, under the assumption that the flavor is equilibrated. So meaning that in order to make this sure, I would need some kind of additional lepton flavor interaction that I test, that I know that, for example, if I have, because of course one wants to make sure that a flavor asymmetry is not stored in another flavor that I don't test, right? And so to say, what we did was mainly focusing on the corresponding flavor that we would have, what we have in the interaction. But of course, for a proper study, one would then also need to take into account lepton flavor interactions. And this is basically what we are currently doing in a UV complete model, to take everything coherently into account. But this, so for now, is just an estimate.
Okay, thank you.
You're welcome.
We have one more question by Matthews.
Hello, can you hear me?
Yes.
Yes.
Thanks, Julia, for the talk. I was wondering if the channel K long to nu var, for example, was accessible, would that provide better constraints than K to pi nu var, let's say if probed at the level of 10⁻⁸ or so?
Okay, I mean, this is, okay, so I'm not sure exactly what you want to compare, but this is basically the values that, wait, I'm going back.
I mean, in terms of the scale of the new physics probed, I imagine that it will probably be similar.
Yeah, so okay, well, I can give you the numbers here. I have to admit, I don't know them by heart. There we go. This is what you're asking for. So here. So in principle, okay, so the problem here is that, okay, so bottom line, you see it's roughly a bit lower than the K plus. But on the other hand,
I mean, actual like K long to nu var without the pion, because I know there have been some ideas recently discussing charge exchange processes to look for K long to nu var. So I was wondering if you looked into that.
No, I mean, I looked into, there was a paper by that I also cited by from 2017 that basically looked, as you said, also in K long or K into neutrinos itself. And they were mainly saying that there are currently really no experiments basically looking into it. So this is the reason why we didn't dig deeper. But of course, if you now say that there's something that, then of course it might, but we simply didn't look at it in more detail.
It's just maybe, you know, the claim was that it could get to levels of 10⁻⁸ with this new technique. So I was wondering if, you know, maybe it's a more sensitive probe.
No, sure. I mean, so, but you say that there, I mean, if you have some link that you can send me with respect to this, I would, because I just looked into it again. And so, for example, there is this, do I have it now here quickly, this paper, what I was citing? This one. Is it here, this paper? Ah, it was 2014. This is basically where they discussed this probe.
Mm-hmm.
And they basically said that, yeah, currently this is basically not experimentally tested.
Mm-hmm. Yeah, but if one could show that the scale that you probe like that is much higher, maybe motivate.
Yeah, sure. I mean, it's a good idea. I think I will have a look. I think it's a fair question.
All right, thank you very much.
Yeah, thank you.
We have one more question by Asma. Asma, let me make you a presenter. Asma, yes.
Hello, do you hear me now?
Yes.
Yes.
Okay. So Julia, I had a similar question. I mean, regarding the pure K-long invisible decay, K-long to neutrino. And in fact, we did it. We did it in 2016. So we addressed also
K-long, yeah.
Pion and neutrino, and also K-long to pure missing energy. And what we found is that we don't gain, we have like processes less than 1% for the like kaon to pion neutrino, LNV or
Second,
LSV. In 2000, yeah, less than 1% from below the standard model. And for the pure, it was in 2016 with Olseer, Sumansari, and Damir Bisile. And we found also that for the pure missing energy, we can have branching ratios as high as 10 to the minus 10.
Yeah, okay, so this was K, you said K long?
Yeah.
Yeah, okay, so I was sorry, I was before thinking only about K plus. Yeah. Okay, but yeah, I'll have a look at it.
Thank you.
Thank you very much.
I actually wanted to ask, so what is the branching fraction in the standard model for the invisible decay?
For the invisible.
It's also maybe a question to Matheus or Asma if they have it.
For the pure invisible is 0. The pure invisible is 0. It's not possible.
Completely 0.
Yeah.
Okay.
Yeah, it's much below 10 to the minus 10. It's neutrino mass suppressed.
Okay. Okay. Well, thank you everybody for coming, and thanks a lot, Julia, for this very nice talk.
Yeah, thanks for all the questions. I will look into it. Thank you very much.
Just a quick reminder for everyone, our next webinar in 2 weeks on the 15th by Gilly Elor. So please, we wait you here. Thank you very much, and bye-bye.